called oxidation numbers. Okay. And to give you a little bit clearer look about what oxidation numbers are, oxidation numbers are similar to charges, but they're not exactly a definite charge, okay? Oxidation numbers can change from compound to compound, and it just has to deal with how they bond and things like that. So I want you to get a little bit clearer understanding, so I want you to turn to page 232, okay, in your textbook, and you're going to read a little bit about oxidation numbers. Okay, so in that paragraph, it tells us that oxidation numbers are kind of hard to describe. Okay, they're not really a charge, but they kind of give us the idea of a charge, but they're not for ionic compounds. It's only for covalent compounds. So that means when we look at oxidation numbers, are we going to be looking at the metals or the nonmetals? The nonmetals, right? Your book calls molecular compounds covalent compounds. Those are the same thing. So when the book says molecular, you can think covalent, right? It's between nonmetals or polyatomic ions, and polyatomic ions are always between nonmetals. Okay, so we're looking at kind of this distribution of electrons, or how the electrons are shared between these two compounds, or these two elements. In covalent compounds, we share electrons. In ionic compounds, we kind of trade them back and forth, and we'll get to that next time when we talk about chapter 6. But essentially, that's what we're looking at. When we look at covalent compounds, we have this sharing of electrons. So sometimes our electrons are shared evenly, and sometimes they're not. So these oxidation numbers give us a little bit better idea of how those electrons are being shared and what's really happening in that compound. Okay? So there's a bunch of rules that go into oxidation numbers. So I'm going to give you the rules first, and then we're going to go through and start kind of identifying oxidation numbers within a compound. Okay? So I'm going to give you this set of rules. There's 7 rules. Okay, 7 rules. And we're going to start listing those, okay? So these are our rules for assigning oxidation numbers. Number 1. Elemental compounds. Things like O2 or S or N or an element that's by itself has an oxidation number of 0. So let me talk a little bit about some elemental compounds, or some things that have to be, that can hang out by themselves, okay? This is kind of a sidestep here, but these compounds are called diatomic. Okay, and what this means is that they can't hang out by themselves. So they have to be 2 atoms, right? These are things like hydrogen, oxygen, nitrogen, and then all of the halogens. So F, Cl, Br, okay, all of the halogens, ... okay? These things don't exist basically in a chemical formula by itself. It would have to be H2, O2, N2. Okay, that's how it goes, and then so on and so on. Okay, so it kind of makes a little 7 there on your periodic table. Okay, nitrogen, oxygen, fluorine, and then the group 7s. Okay, or 17s. And then hydrogen is also grouped with that. Those are called diatomics. So if you see them paired, H2, O2, N2, they have to be that way. You would never see a hydrogen atom hanging out by itself. Okay? Can we think about why we might not have a hydrogen atom hanging out by itself? When hydrogen hangs out, it's usually an H+, right? So what would happen with that? Yeah, something would want to pick up that proton, right? We talked about proton donors and proton acceptors. Something's going to want to snatch that up. So if it hangs out H2, it's a little bit safer. All right? That was kind of a sidestep, but these are elemental. So these diatomics would all have an oxidation number of 0. Okay? All right, very good. Rule number 2. Fluorine always has an oxidation number of -1. Always. Fluorine always gets to keep its charge as its oxidation number. Can anyone guess why fluorine might be the one that gets to do that? Yeah, what do you think?
Because it's like the base of the halogen and it's the most volatile.
Yeah, pretty good. The most electronegative. Have we talked about electronegativity in here? Not a whole lot? Okay, that's not ringing any bells. Okay, that's fine. Electronegativity is how badly it wants to take in other electrons. How badly it wants to collect electrons. And fluorine is the most electronegative atom. It wants to take it the most. So fluorine always gets to keep its charge. When it shares, it's never going to share evenly. It's always going to take electrons. Okay, it's like the greedy little kid. Okay, has to take more than anyone else. So that fluorine atom always gets to keep its charge as its oxidation number. Okay, so if fluorine is paired with anything, you know fluorine's oxidation number is -1. Rule number 3. Oxygen has an oxidation number of -2 unless it's bonded with fluorine. Okay. So unless it's bonded with fluorine, it has a charge. It has an oxidation number. of -2. So oxygen is really close to fluorine. That means it's probably got a pretty high electronegativity as well. So it's going to get to keep its charge most of the time. Okay, unless it's bonded with fluorine, which doesn't happen all that often, but okay. Okay. Number 4. Hydrogen has an oxidation number of +1. And this is almost always true. Okay, the only exception is unless it's bonded with a metal, in which case it's -1. Okay, but we're really only going to be looking at covalent compounds. So this exception is not going to come into play hardly ever, right? Because we're really looking at the non-metals here. So hydrogen almost always has an oxidation number of +1. So those are the big 3 really that get to keep their charge. Okay? Fluorine, oxygen, hydrogen. They get to keep their regular charge as their oxidation number 99% of the time. Okay? After that, then we can start seeing some changes. Okay? Any questions so far? Okay, let's look at our next rule, number 5. The oxidation numbers in a compound must add up to 0 in a neutral atom. Sorry, in a neutral compound. I don't know why I said atom. So if our compound is a neutral, has a 0 charge overall, that means our oxidation numbers need to add up to 0 overall. If our compound has a charge, then it must add up to the charge. Okay, that's our next rule. So oxidation numbers in a compound must add up to 0 in a neutral compound, or oxidation numbers must add up to the correct charge of the ion. Okay, and what is the definition of an ion? Any ion, what's the definition of it? Yeah, it doesn't. It's not neutral. It has a charge, right? An ion in and of itself is a charged particle. Okay, so if we've got a polyatomic ion per se, polyatomic ions have a charge. So if we're looking at the oxidation numbers in a polyatomic ion, those oxidation numbers would need to add up to the correct charge of that compound. Okay. All right, and our last rule here, number 7, says the most, if none of those other rules apply, if oxygen's not there, if fluorine's not there, if none of those other rules apply, the most electronegative atom gets to keep its charge. So when we're talking about electronegativity and we look at our periodic table, does the group 1s, what is their charge most of the time? +1. So do they want to give up an electron or do they want to take an electron? Yeah, they want to give up their electron, right? That's how they get a +1 charge, because they've got one valence electron. So they have one valence electron, they want to give it up, is what leaves them with a +1 charge. Okay, how many valence electrons does group 7 have? Or 17? It has 7 valence electrons. Okay, so what does it want to do most of the time? It wants to take an electron, which gives it an overall, usually of a -1 charge. Okay, so out of these compounds, fluorine, it's closest to the nucleus, right? Because it's on the lowest energy level. Do you remember talking about that? Fluorine's on the lowest energy level, and it's got 7 valence electrons. So fluorine wants to take electrons more than any other element. Okay? From there, the pattern kind of goes like this. Okay, we kind of just spread outward from fluorine. So basically, the closer to fluorine, that means the more electronegative. Okay, so you might want to write that down. Closer to fluorine equals higher electronegativity. Okay, and that's basically where you need to be at for right now. We're going to cover electronegativity a lot more in Chapter 6, but this is kind of the base of where you need to be right now. Okay, so if you have to think about it, if you've got 2 compounds and you can't decide which one's more electronegative, you need to look. The one closer to fluorine is probably going to get to keep its charge as its oxidation number. Does that make sense? So we need to know the charges for those groups. Okay, so group 17 we said has a -1 charge. What does group 16 have? -2 and then -3. These guys are a little bit more, flexible. But then over here we jump to +1, +2, and this one's mostly +3. Okay, you got that periodic table of ions in with you, but that's how we kind of determine that. Okay? Let's go ahead and try some examples here with oxidation numbers. Okay, we're going to start with a pretty simple one. Okay, let's say that I have a compound UF6. Okay, and we want to determine the oxidation number for each of these. Okay, is this compound a neutral compound? We don't see any charge hanging out up here, do we? No, so it's neutral. So that means that our oxidation numbers need to add up to 0. Wow, I just cannot spell today. Okay, need to add up to 0. So what do we know about fluorine's oxidation number? Always. It's always -1. It always gets to keep its charge, right? It's the most electronegative element, so we have to know that. So I like to just put usually their oxidation number up on the top. There's no set rule for this. This is just kind of how I work it out. And then I like to put the total on the bottom right here. Okay, so if I have 6 fluorine atoms, each with an oxidation number of -1, what's my total need to be down at the bottom? -6. Okay, and if I want my total to add up to 0, what do I need my other element, which is uranium. Okay, thank you. I couldn't remember if that was you or you are. Okay, that means I need uranium to add up to a total of what? +6. And how many uranium atoms do I have? 1. So that means the oxidation number for uranium has to be +6. So your oxidation numbers are up here at the top. Okay, it's not the totals we see at the bottom. It's the oxidation numbers we put up here at the top. Again, it's not a rule that you need to put the oxidation numbers at the top. It's not a rule that you need to even write it out like this. Okay, that's just kind of how I work through that. That's up to you. If you find a different system that works better for you, that's great. Okay? So if I asked you for the oxidation number of uranium, in this case you would tell me +6. It's really important you include the positive sign, use the plus. And then for fluorine's oxidation number, you would tell me -1, not -6. Okay, it's each individual atom that you're looking for this oxidation number for. Okay, it's not fluorine as a whole, it's each individual fluorine atom has an oxidation number of -1. Okay, feeling good? It's not too bad, right? Let's try another one here. First, name this molecule. Okay, the H is first. What does that tell us? It's an acid. And then we look at what anion does it come from? Sulfate. So that means it's called sulfuric acid. Very good. Okay, now back to our oxidation numbers. When we work these oxidation numbers, you kind of go with the rules. Start with the rules, okay? So we don't have fluorine, so that doesn't tell us anything. What do we know about oxygen? It's usually -2, right? Usually a -2. If it's not bonded with fluorine, it's a -2. So we've got -2 of these. We've got 4 oxygen atoms, so that means down here we've got a -8 total. What is our whole compound going to have to add up to? 0, because it's a neutral. Okay, so now we're stuck. We've got 2 things combined that we need to add up to +8. Do we have a rule for hydrogen? Always a +1 unless it's bonded with a metal, and that's not the case here. So hydrogen has an oxidation number of +1, and we've got 2 of those hydrogens, which means this is a +2. So +2 plus x minus 8 equals 0. So what does x have to be?
6.
Good, 6. Okay, so now we take a look at sulfur. So how many sulfur atoms do I have? 1, and I need it to add up to +6. So that means the oxidation number of sulfur here is +6. All right, so when we're doing these, I want you to make sure you circle those oxidation numbers so I can tell you're not trying to tell me that hydrogen's oxidation number is -2. Or +2. That's not how it works, right? I want you to make sure you give me a good identifiable oxidation number. They're not the totals. Bless you. This time I want you to try and give me the oxidation numbers for chlorate. First of all, you got to figure out what chlorate is. What's the compound for chlorate? ClO3 minus 1. So now we're dealing with one that has a charge. Exactly. We're not going to set it equal to 0. We're going to set it equal to -1. So we've only got 2 elements here. Oxygen we know has usually an oxidation number of... No. -2. -2. And we have 3 oxygens. So that gives me a -6. I don't want it to add up to 0 this time because I have a charge on my whole compound. So it's not a neutral anymore. It's got a charge. So that means I want the whole thing to add up to -1. So what does that mean my chlorine has to be? +5. I've only got 1 chlorine atom right here, right? No subscript, which means 1 chlorine atom, which means chlorine's oxidation number is +5. Okay. So when we're doing these problems, if you don't rewrite them like chlorine equals +5 and oxygen equals -2, then you need to make sure that you circle those answers, because if you leave me something that looks like this, ClO3 minus -2 plus 5 plus 5 plus -6, I don't know what those numbers, I don't know which one you're trying to tell me is the oxidation number. Okay, so you can't just leave me something that looks like this. You need to make sure you either circle that answer or you rewrite it out to the side, okay, with each individual atom's oxidation number. All right. All right, you ready to try some on your own? Okay, I'm going to give you a few here that we can do on our own. I want you just for fun to name them too, because we know how to do that. We do know how to do that. You should know how to do that. Okay, so let's try those on your own. That is an O, yes. Jenna, what do you think? Hydrochloric acid. Perfect. Okay, let's talk about the oxidation number. So the oxidation number for hydrogen. Okay, what do we have as a, you could say it all together. What's the hydrogen's oxidation number? +1. And chlorine's oxidation number is? -1. Good. Easy, easy. Okay, because there was no fluorine in it, because there was no oxygen in it, we go to our hydrogen rule. Hydrogen is +1, and we need our overall compound to be neutral, which means chlorine's -1. This kind of follows our other rule too, because chlorine is really close to fluorine, which means it gets to keep its charge as its oxidation number, so it's -1 still. Okay? Go with the hydrogen rule first, and then if there's no, this one just happens to go under both. Yeah. Okay, next compound, what's the name? Alex, what do you think the name is?
Carbon tetrafluoride.
Perfect. Carbon tetrafluoride. Not monocarbon tetrafluoride, right? Just carbon tetrafluoride. Good. Okay, carbon's oxidation number is? +4. Good. And fluorine's is? -1. Very good. Okay. Everyone agreeing with those so far? Good. Our last one. The name for it. Cece, what'd you have? Tetraphosphorus decoxide, right? Decoxide. Right, we're going to drop that A for deca. Good. Okay, and the charge, or I'm sorry, not the charge, the oxidation number for phosphorus is equal to +5, and the oxidation number for oxygen is equal to -2. We're going to keep oxygen's -2 as its oxidation number, right? -2, which gives us a -20. We want this to equal 0. So that means we're going to have a +20 here. We've got 4 of them, which would give us a +5. Okay? Uh-huh.
So if you don't know either one of the charges, well not the charges, but the oxidation numbers of the ions, then is it just the atom's charge?
Uh-huh. So if we had one that's, let's go with one that doesn't have oxygen or fluorine or hydrogen in it. Okay, so let's try one. Okay, this one now doesn't have fluorine or oxygen or hydrogen in it. So then we go to our rule that says the most electronegative gets to keep its charge as its oxidation number. So which one of these is closest to fluorine? Chlorine is the closest to fluorine. So that means chlorine would get to keep its charge, which is -1 as its oxidation number. We'd have a -4 down here. Would we want it to equal 0? Yes, because that is a neutral atom. Okay, which means we need a +4 total, and we only have one phosphorus, so phosphorus's oxidation number would be +4. Okay, does that make sense? Okay. And if we follow the rules with our naming, we know the least electronegative goes first and the most electronegative goes second. So if you don't have them in there, it's usually going to be your last element that gets to keep its charge too. Okay, if you think about it that way, it's usually going to be the last one. Okay? Any other questions with oxidation numbers?